Good morning, everybody. So these are the survivors, huh? You've survived two things.
Physics.
The exam and the water mains. Yes? No? Yeah. About the water mains, I apologize. The sabotage operation that the faculty was running was unsuccessful. We were going for the entire campus, not just a part of it. No. In case you haven't heard, a car lost control Sunday evening and sheared off the water mains that had come up above the ground near the old administration building. So out of control car breaks the mains, right? And there's no more water to all of campus on the other side of the tracks. So that's what happened. The semi-official word I've gotten from people that would know, but they're just not telling everybody, is that the main has been fixed. Like all the parts came, they've dug everything up, they fixed it, but unfortunately they have to like flush all the lines and then chlorinate all the lines and then let it sit for 24 hours and then like test just to make sure that the water quality is okay. So like that's why we got the message about Monday, but then like Tuesday and Wednesday, like, you know, both days. But we're here, right? We're doing it still. The exam. So tomorrow's the day, right? And I don't know how to communicate this other than to say, don't miss tomorrow. Like exam autopsies are just as important as the actual exam themselves. And there's more information, if you want a sneak peek, there's more information in the syllabus about what the exam autopsy is going to be like. But tomorrow, I actually am going to spend some time trying to walk you through not just how I graded it, but like why the grade on your exam isn't as bad as you think it might be initially, all that kind of stuff. So tomorrow's an important day. Don't miss it. Future test autopsies, I don't need to explain much. I just need to give the exam back and then you know what to do. But you'll have some stuff to do. You'll be reworking problems that you missed tomorrow, all that sort of stuff. You won't know your score until you get that exam in your hand. Part of the reason there is so that you are among friends when you get the disappointing news, right? And we can all support each other and all that kind of stuff. So, but in spite of all that, in spite of broken water mains and exams coming back tomorrow, we have to move forward. This unit, right, is chapters 4, 5, and 6. 4 and 5 are kind of the same thing. They're Newton's laws and why things move. And in chapter 6, we're going to do everything that we've done before. So projectile motion, Newton's laws, all that stuff, from a different point of view, and that point of view is called conservation of energy. But that's kind of getting ahead of the story. We still need to survive Newton's laws. This week, so today and Thursday on chapter 4, next week on chapter 5, and the week after that on chapter 6. And then review, exam.
When it comes to the questions on the exam that are going to be for the unit 2,
Yeah.
Are you saying that it's going to be specific to 4, 5, and 6, or it's going to
Yes.
be a combination of 1, 2, 3, and 4?
It's going to be specific to 4, 5, and 6, but as you'll see, we can't do 4, 5, and 6 but without 1, 2, and 3. Because like we're about to start using vectors in ways that you guys don't want to know. So like just vectors are here to stay, all that kind of stuff. So yeah, it's a ladder, right? I'm not going to explicitly go back and put a chapter 1 problem on the next unit exam. But do you need to know how to convert units? So that's what's going to happen. I don't know about you, but this guy looks like a freak. Like it's the eyes, isn't it? I don't know if the artist did a good job of capturing the likeness of the man, but
I found this on the web for I don't know. Check it out.
oh, awesome. Siri will teach the class now. But like, so does anybody know who Alexander Pope was? Did you guys have, okay, Alexander Pope was one of those people you ignored in your English class in high school. Wasn't ever mentioned? He probably was. You probably were tortured with some of his poetry. He was an English poet and author contemporary of Newton. So this is like the 1700s, and pretty famous. Like he's kind of up there with Shakespeare and all that kind of stuff. And Alexander Pope had a little bit of a sense of humor, and he wrote a little limerick about Newton. Newton was very much alive at the time. And Alexander Pope said this. He said, "Nature and nature's laws lay hid in night. God said, 'Let Newton be,' and all was light." Isaac Newton is like synonymous with physics. We do credit Isaac Newton with inventing physics. Before Isaac Newton, there was this natural science, there was this natural philosophy, there was this idea that a scientist was kind of doing everything, the chemistry, the physics, the geology, those things that we would think about today as being separate branches of science. They were kind of all together. And after Newton, well, that's where modern science really started to separate out and get all of these different topics. The laws of motions we're going to study today, basically all of chapters 4, 5, and 6, are more or less his fault. There are other people that probably deserve a little bit of credit. But Newton really is a beginning of our modern understanding of why the universe does what it does. I do want to point out that Newton was an absolute jerk. Genius, but terrible to the people around him. He spent most of his career suppressing the work of others who disagreed with him. That was like his main focus in life. Okay? In fact, his genius in understanding how the universe worked and why it did what it did was a very minor part of his life. And it's kind of weird to say that, but we've been through a pandemic. Imagine, so Newton went through a pandemic too, right? Does anybody know what pandemic Newton went through? Black Death, okay? And so people are dying left and right from the bubonic plague. So Newton goes to the country where the plague wasn't nearly as bad as it was in London. School's out, and what would you, okay, we're in lockdown, right? Okay, you can't go to work. What would you do?
Die.
Okay, besides that. You probably wouldn't sit there and invent a whole new branch of mathematics called calculus so that you could do physics problems, right? It probably wouldn't enter, right? You probably wouldn't sit down and conceive of four laws that would help people 300 years later get to the moon, right? That probably wouldn't be your... I was playing video games and madly trying to put all my physics classes online, right? So this is what Newton did. But then he did that for a period of about 2 or 3 years, and then he just didn't do any more physics. He went off and ruthlessly suppressed other people that didn't agree with him. He was an alchemist. He was searching for the alchemist's stone. He was trying to gain immortality. He would put knitting needles into his eyeball just to see what it felt like. This guy was not right. He really wasn't right, okay? But genius, yeah. So we honor Newton by talking about his laws. I'm not sure that we should ever really honor the man, but he did have his influence. And we take basically all of our modern understanding of how things work from his initial statements. Does anybody know what the first law is? Yeah, things that are in motion stay in motion, things that are at rest stay at rest. Okay. There's some implications there, right? Okay. Now, what we're going to do is we're going to do them slightly out of order. We're going to do the first law, then the third law, then come back to the second, because the second law is where all of our math is going to happen. But the first law does bring up this idea of motion, and we've already studied what motion is, like we did kinematics, and so that's like velocity, right? Something moving has velocity, it has position. A change in motion is not velocity, that's an acceleration. But Newton's first law brings up a term which is a little bit funky, and it's defined by kind of what it isn't. And it's the term called inertia. I'm not going to ask you what inertia is yet. You probably know. What has more inertia? A bicycle or a car? Car. How did you know that? Inertia is not mass. Mass and inertia are kind of related to each other in that the more mass something has, the more inertia it's going to have. Okay? But inertia in and of itself is not mass, and it's also not weight. More on that later. Okay? But inertia, again, is one of those, it's one of these ideas that like everybody kind of really like knows, you've experienced it, right? But what is it about the car that tells you it has more inertia?
It moves faster.
Okay, you use the F word. Yeah, okay. What's a force? Good. Say that really loud. A push or a pull. That's it. When we are in the weeds of physics and we're like lying on the ground bleeding out, right? And we can't remember what we're doing. I need you to remember that a force is a push or a pull. That's all a force is. It's a push or a pull. And inertia is that thing about stuff that resists that force. The more inertia something has, the more push or pull it takes to get it to do something, right? So when your friend's car stalls in the intersection and you have to jump out and why is it your friend never says, hey, you know what, I'll get out and push, you drive? It's never like that, right? It's like, go get out, push, right? You just know, right, that pushing that car is going to take a lot more effort, a lot more force, a lot more push, even to just get it going slowly, right? Compared to a bicycle, where you're like, whee, right? So inertia is a measure of how much something resists a change in its motion. Changes in motion are brought about by forces, and Newton's first law is trying to capture this idea that things want to keep doing what they're doing. Always. And this is going to sound a little bit broken because you've had experience to the contrary. If you're driving along in your car at 65 miles an hour on the freeway and you let off the gas pedal, does your car keep going? No, it slows down. So did we just break Newton's first law? No. There's a really important like little statement at the end of Newton's first law. It's this external force thing, right? Okay. Things want to keep doing what they're doing as long as they are not pushed or pulled on. Sometimes the language is really fancy, acted upon by an external force, right? But basically, things will keep doing what they're doing. And if they're just sitting there like my iPad, is this a state of motion? Yes. It happens to be zero velocity, right? But it is nonetheless a state of motion in that we can quantify that it's not moving, right? Has a velocity of 0. So my iPad is going to stay here doing this until what happens?
You push it.
I push or pull it somehow, right? To change its state of motion. Lift it up, put it down, slide it, whatever it is I'm going to do. Your car, though, doesn't keep going. Why not? There is an external force now. You take your foot off the gas and it starts to slow down. So where's the push or pull coming from?
Friction.
Another F word. Okay? Friction in this case, which is the one you're really going to start cursing about. But we'll get there later. So yeah, Newton's first law, things want to keep going or they want to stay at rest unless something comes along and pushes or pulls on them. Okay, so that's the first law. And inertia is a killer. Not that this has anything to do with death, but you've probably seen this trick done before.
We'll try to remove the tablecloth from under these dishes without making a mess. How? By yanking the cloth out very setting moves, this will have to be done much more quickly.
Candles, very important.
The tube wrapped inside the loose edge of the cloth provides a firm grip for a fast pull. When the cloth is yanked out fast, the dishes barely move.
Okay. Do not attempt this at home. But if you do, did you notice the very important piece of equipment that was present? No, well, yeah, but no. What part of the tablecloth is the most important part? The stick that was in the edge of the tablecloth. If you grab a tablecloth at one point and just pull, then there are lots of vector directions there, okay? You're pulling one part, and so different parts of the tablecloth are moving at different speeds and in different directions. And all that's going to happen is that your mom's dishes are going to crash together, and you're going to be in big trouble, okay? So if you ever try to pull this one off, make sure that you put like a broom handle in the edge of the tablecloth, and you like yank really fast and get the entire tablecloth moving at the same time, at the same speed, right? So why did the dishes initially like go with the tablecloth? Well, obviously they were being pushed or pulled on, right? Because they changed their motion. Do the dishes have inertia? Yeah, they do. Okay. Newton's first law says that they just want to stay where they are, right? Even though the tablecloth is getting pulled out. But there is that initial, like, if a push or a pull happens slowly enough, sometimes you can work with the inertia. But if you go fast enough, did the plates and everything stay where they were? Well, they fell slightly, right? But like they really just stayed where they were because they had inertia, right? All right. Let's do third law. Yeah, third law. Okay. So again, we're skipping the second because we're going to spend the next 2 weeks talking about the second law. But let's tackle the third law. Does anybody know what it is? This is kind of the famous one. Equal, opposite, reactive. For every action, there's an equal and opposite reaction. Those are fancy. Let's put that into real words. What's an action? It's a push or a pull. It's a force. Okay? So for every force, right, if an object exerts a force on something else, what do we know about those forces? 2 things. They're equal force, but the directions are opposite each other. Okay. We got to untie this. I want you to do something right. Put your pencils down. Take your fingers out, okay? And I want you to introduce yourself to the person next to you in case you don't know them, right? And then very importantly, ask for permission, okay, to perform the following experiment, okay? I want you to poke them in the shoulder, and then I want you to let them poke you back. Be gentle, ask for permission, go.
I'm gonna forget, but
Okay, all right. Stop touching each other. All right. What did you experience?
Poking someone.
Something really uncomfortable, Mr. Bailey. Some of you are kind of, it felt kind of good. You pushed on them, right? And how much did the person push back? Mr. Bailey, they pushed harder than I did. I'm not talking about them turning around and poking you, right? I'm talking about when you pushed on them with a certain amount of force, okay? What do you know about the force they immediately were giving back to you? It was equal Newton's third law says that when you poke somebody, you're pushing in on them, but they're pushing back on you with exactly the same amount of force. Different direction, right? You're poking in and they're pushing out, okay? They might turn around and go, huh, right? Right? But that's different. That's a different interaction, right? But no matter how hard or little they push on you, you are pushing back with exactly the same amount of force. Yes.
If we're using the same instance, if let's say we push an individual, they're giving back the same amount of force, but opposite. But is there a point in which that force is not equal and we continue? If we
Okay. All right. Hold that thought, Griffin. I need a volunteer. I promise you won't get hurt. And you need to be able to very briefly lift about 175 pounds. Any takers? It's, I know your name, Drew, right?
Yes.
Haha! I can remember some stuff. All right, Drew, come on up here, Drew. Thank you. Okay. All right, Drew, face the class. Do they look scary?
No.
Yeah, they're pretty good looking. Would you please pick yourself up? So good try, right? Okay, I would have gone for the. Nope, not working. Can you pick me up? Whee! Hey, put me down. Give me a hand, everybody. Thank you, Drew. Okay, so why were Drew and I not able to pick ourselves up? Okay, you went immediately to push, scissors, pulls. That's interesting. Why was Drew able to pick me up? No, there's something really significantly different between those two things. Close. Internal force. No. Okay. Let me give you a different way of thinking about Newton's third law. Okay, this is an alternate definition, right? Newton's third law tells us that you can't pick yourself up. What? Well, of course you. Okay, but okay. So what about this? Is that picking yourself up? No, it's called jumping, right? Okay. What's different about this versus this? Think about the number of objects involved. How many objects are there when you're trying to pick yourself up? Just one. But if Drew's picking me up, there's two. Can you name them? Drew and Mr. Balogh, right? When you jump off the floor, how many objects are there? Two. You and the floor, right? Okay. So one way to think about Newton's third law, remember Newton's third law tells us that the forces are equal and opposite, but it is necessary that there be two objects present in order for that force to exist. Forces exist in pairs. That's the key to Newton's third law. Forces are the result of two objects interacting with each other. An object cannot exert a force on itself. And I know some of you are sitting there right now going, wait a second, Mr. Balogh, if I take my fist and I ram it into my face, that's two objects. Okay? Your head and your fist. Yes, they're connected to you, right? And so if you think about your whole body, there's no external forces and therefore no external objects, but you'll still have a concussion, right? So do you, I can give you a guaranteed, sure-fire way to remember Newton's third law for forever. To remember this need for two objects and that they're equal and opposite and all that kind of stuff. I can teach you this. I can give you a method for always remembering this, but it comes with a price. I need you to be willing to pay it before I can tell you what it is. So, let's see. I'm asking you to trust me, which you can trust me with your lives, but I do lie to you sometimes, just to protect you, protect the innocent. I need you to trust me, but I can't teach you this unless everybody agrees to it without knowing what it is. So in other words, are you willing to trust me, and can I teach you this thing?
Sure.
Yeah? Okay, for those of you that are shaking your head, you didn't say anything, so we'll just assume you said yes. Okay? The doors are closed, which is good thing, okay? So I need you to do exactly what I tell you to do for the next 2 minutes, okay? I just need you to commit right now that you will trust me and you will do exactly what I tell you for the next 2 minutes. It's not indecent, don't worry, okay? But I just need you to follow instructions and do exactly what I say. Is that okay? You want to trust me?
Yes.
I haven't let you down yet, right? Okay. I'm going to teach you, and we are going to sing the Newton's third law song.
Oh, no.
You're going to sing out loud, okay? I'm going to demonstrate the Newton's third law song. We are going to sing it together, and then we will talk about later why this is going to work every single time. Okay, you ready? To do the Newton's third law song, I need two objects. I need the chair and the Mr. Balogh, okay? Right? And so two objects are pushing and pulling on each other, right? And so how am I going to sort out Newton's third law and those two objects and remember everything that I need to remember? I am going to sing the following song. You guys will repeat with me the song after I sing it. Those of you who are still conscious after listening to my singing voice. Okay, you ready? This is how the song goes. If the chair exerts a force upon the Mr. Balogh, then the Mr. Balogh exerts a force upon the chair. No clapping? No, that is too late. That is F's. You all get F's. All right, let's sing the song together, right? And sing the chair first. Are you ready? If the chair exerts the force upon the Mr. Balogh, then the... That was awful. That was... Okay, come on. Your best in the shower voices, okay? Because that's where all Americans sing, right? Okay? Yeah, no, right? Okay, the singing, gotta sing, you promised. Okay, right? Let's do the pencil and the table. Okay, and sing table first. Are you ready? If the table exerts a force upon the pencil, then the pencil exerts force upon the table. That was better. You're getting better. Okay, now, what does the song remind us of?
Two forces must exist.
Two things, two objects, right, are in the song. And the one object exerts a force upon the other, and then the second one exerts a force upon the first, right? So the song reminds us of two objects being necessary for forces to exist, and that those forces will be equal and opposite. This is the essence of Newton's third law. Why are you going to remember this for forever?
Because we are embarrassing ourselves.
Yeah, the psychological trauma of having to sing in public is going to have this burned into your brain. Like, I've watched students taking exams start humming to themselves. Right? I have to kind of walk over and go, right? Or sometimes, Mr. Balogh, I'm not sure what this question is asking, and I'll just be like, sing it. And it comes flooding back, all the trauma, all the embarrassment. Let me give you two pieces of life advice, really quick, tangent here, right? Okay. Nobody is watching you when you dance. Just dance. Nobody's listening to you when you sing. Just sing. It'll make your life better. All right. Yeah. If it's got a fire extinguisher, it's going to be fun, right?
The spray from a carbon dioxide fire extinguisher looks a lot like the exhaust of a rocket. And like a real rocket exhaust, the escaping CO2 can accelerate a large mass. We'll use this extinguisher mounted on a rolling wagon to accelerate a person to suborbital speed. 3, 2, 1, blast off. Engine cut off.
Okay, number one, she wasn't a very large mass. In real life, she's like that big. Number two, what pushed on what? What were the two objects that caused this change in motion? Oh, the extinguisher and the wheels? Carbon dioxide and the oxygen in the air? I'm not allowed to show you this clip because of copyright reasons. But in the Pixar movie WALL-E. WALL-E.
Oh yeah, he's in the outer space.
Okay, spoiler alert.
Oh, sorry. Guys.
WALL-E dies.
What?
Okay? So I know. It's a big spoiler, right? At least that's what we are led to believe because he's in an escape pod. WALL-E's a robot. And he's in an escape pod. And the escape pod blows up. And his girlfriend, not girlfriend, whatever she is, right? Okay, sees this happening and gets very sad, right? Because WALL-E's dead. But then suddenly WALL-E comes flying out of the wreckage of the escape pod holding a fire extinguisher. Okay? So like this fire extinguisher, it's squirting something, right? It's pushing carbon dioxide out, right? Okay? If WALL-E wants to go to the right, which way does WALL-E point the fire extinguisher? To the left. So, WALL-E squeezes the fire extinguisher handle, and the WALL-E fire extinguisher combo shoots carbon dioxide gas which way? To the left. In other words, WALL-E pushes carbon dioxide to the left. And what does the carbon dioxide do? Pushes WALL-E to the right. And if WALL-E wants to come to a stop, if he's moving to the right and he wants to come to a stop, he points it to the right so that pushing the carbon dioxide out to the right means that the carbon dioxide will push him left and slow him down. Okay? I won't make you sing the song, but what are the two objects? WALL-E and the carbon dioxide. Right? So in this example right here, it was the wagon and the carbon dioxide. Notice there's no mention of the ground there. What? You already know the answer to this question. What's the force between the ground and the wagon? There's gravity in there, isn't there? It's not quite right. Gravity's what's pulling the wagon down. Okay? But there's another force, a contact force, a normal force, between the wagon and the ground. We'll get to that in a bit. Okay? But in order for that wagon to get going, in order for WALL-E to get going, you don't need the ground to be there. How do you... Okay, this is now rocket science. How do you launch a rocket? Pointy end up. Explodey end down. Key part of rocket science, right? Okay. What does the explodey end do? It pushes what? It pushes the fuel, the propellant, right? Which way? Down. It pushes the propellant down. What does the propellant do? Pushes the rocket up. This is what Newton's third law is trying to get us to think about. Does the tower need to be there? Does the ground need to be there? Does the earth need to be there? No. None of that needs to be there. All that matters is that the rocket is pushing something down, and that something is going to do what? Push the rocket up. Newton's third law. So Newton's third law is equal and opposite forces. It's two objects are required for a force to exist. It's the law that says you can't pick yourself up. It's all of those things. Okay. Now we come to it. I can't protect you anymore. We got to do Newton's second law. Okay. I'm going to write Newton's second law the way I want to. There's lots of ways to write Newton's second. Well, actually, there's not lots. There's 3 ways to write Newton's second law. But I'm going to write it the way that I like to write it. This is how I like to write it. And the reason for that will become clear probably on Thursday.
Is that a Z or a 2?
It's not a Z, and it's not a 2. Yeah, what is this symbol right here? It's a big Greek capital sigma. And you've probably seen that in your math classes, right? No? No? Never saw this in your math classes? I don't know. Calculus? No, you did sums before calculus, didn't you? Okay. Maybe some of you haven't seen it. It means add up. It means the sum of. Sum as in S-U-M, right? Adding things together. So when you see that symbol in front of an F, what do you think the symbol F is? It's the force, right? And what's the little thing above the F? It's a vector. Are forces vectors? Yeah, they're pushes or pulls. Do their directions matter? Totally, right? Okay. All right, what's the A? Acceleration. What's acceleration?
Negative 9.8.
Nope, it's not negative 9.8. That's a very special one. It's a change in motion. Try to remember that. You're going to want to revert to bad water. Okay? Acceleration is a change in motion. What causes acceleration? A non-zero net force. This sum of forces is also called the net force. Okay? We'll say net force. Not as in like basketball and it was all net, but net as in the total amount. Okay? So what happens if the sum of all forces or the net force is 0? There's no change in motion. Right? A lot of you may have encountered this. You probably have encountered this one. Right? It's the same thing, isn't it? I just wrote mine backwards. Actually, I wrote mine forwards. Everybody else is backwards. You'll see why. I'm trying to trick your brain into doing something. Okay, later. So let's do an experiment. I'm going to run as fast as I can into that wall. Okay? I'm going to run as fast as I can into that wall, and I'm going to have no fear. Because, according to Newton's third law, what do I know? The force between me and the wall, two objects interacting, has to be what? The same magnitude and opposite directions. So no matter what, I can't get hurt. No matter how hard I try, the building cannot exert more force on me than I am exerting on it. So we see what happens? Students always want to see their teachers harmed in some way, shape, or form, right? Okay? But if I ran as fast as I could into this wall and didn't slow down before getting there, who would win? The wall, right? The wall would win. Is it true that the forces are equal? Yes. What is not true? That I would be safe. The masses are different. Which one has more mass, me or the wall? Be careful. The wall. Okay? The wall has more mass. Does that mean it exerts more force? No, it's the same force. So what's different?
You are exerting force on the wall.
No, what's different? If the mass is different and the force is the same, the acceleration has to be different. The acceleration, the change in motion. If I run full tilt into the wall, does the wall's motion change? No. Does mine? Okay. Forces between two objects that are interacting are always the same magnitude. Newton's third law. Directions are opposite of each other. But Newton's second law tells us how mass and acceleration are playing around with that. There's a soccer ball on the floor. If I run up and I kick the soccer ball, which one experienced more force, me or the soccer ball? The answer is neither. The answer is the force is the same. But Mr. Balogh, the ball, it obviously experienced more force. No, it did not. It can't. The universe is not built that way. The universe is built such that when two objects okay, let's sing the song. Mr. Balogh and the soccer ball. Okay, are you ready? No. Sing Mr. Balogh first. I don't care, Drew. Right? Okay, ready? If Mr. Balogh exerts a force upon the ball, then the... You're degrading. Okay? Good thing this is not a singing class, right? But the force is the same. That's what that song's trying to remind us of, right? But what's different? The acceleration, the change in motion. How much did my velocity change? It didn't, right? What did the soccer ball do? 0 to, right? Why? Why was the soccer ball's change in motion so much bigger than mine? Thank you for saying it had a smaller mass and I didn't have a bigger one, right? So it's that mass. What does Newton's second law tell you? Are there any words?
No.
There's no words to Newton. I mean, you could say that the mass and the acceleration are proportional to each other through the force. You're just saying math, right? Okay. Newton's second law is a statement of the relationship between mass, acceleration, and force. Let's talk about what it isn't. What is a force? Good. I'm pointing up here, but a force is a push or a pull. You guys remembered I said that we have to hold on to that idea, right? So many people come into my class and go out of the door thinking that a force is m times a. It's not. What's a force? It's a push or a pull. What's ma? I don't know. But I do know that mass, acceleration, and force are proportional to each other. What's mass? It's not weight. Weight is a push or a pull that is very specific to Earth for now. Okay? We'll go to other planets later. But weight is the force of gravity acting on you. That's where your weight comes from. It's a push or a pull. In this case, the Earth pulling on you? We need to sing the song again.
Please no.
Yes,
Please have
it helps so much. Let's sing If the Earth Exerts a Force Upon the Me. You ready? If the earth exerts a force upon the me, then the... Really? The me exerts a force upon the earth? You ready? You ready? Ready? Wait for it. See if you can feel it. Ready? Thank you. Did I just pull on the earth?
you pushed on it.
Well, I pushed first, but don't think about that. Did I just pull on the earth? Did the earth pull on me?
Yes.
So did I pull on the earth?
Yes.
Yeah, how many objects? What's the force? Why didn't the earth go anywhere? Way more mass. 5 point something something times 10 to the 24 kilograms more than my 80 kilograms.
So what you just did, there's no, like even with the smallest degree, there's not a single inch of the earth moving the slightest.
Okay, probably a picometer, but 10 to the minus 12 meters. But very difficult to measure. But you haven't answered my question. What's mass?
How much matter something has?
Okay.
Amount of molecules within them.
Yeah, well, how much matter something has? So that kind of is talking about like volume a little bit. So that's like a little bit more like density, maybe? Ren's not far off. What's mass?
How much matter something displaces?
Again, that's like a volume, right? The implication there is that like it's taking up some amount of space, right? So yeah, displacement.
Is it like how hard it is to move it?
So you're kind of going back to the first law, like inertia-ish kinds of ideas, because we know that the more inertia it has, the more mass something has. You're close. You're circling, but you're not landing.
The resistance to gravity?
Oh, that's weight or inertia. Why can't you tell me what mass is? Because it's a government conspiracy. No, this is not a class of conspiracies. Do you know what mass is? I thought I did when I came in, Mr. Balogh, but now you're looking at me funny. You know what mass is. I know you know what mass is. But you can't describe it to me because it's indescribable. What do you mean it's indescribable? I'm going to do an analogy. This one's not going to be very hard. Let's just pretend for just a second that I am from another planet. Told you it wasn't going to be hard. And on my planet, we can't smell or taste anything. Like my species, we lack the chemical receptors to be able to taste or smell anything. I would like you human beings to tell me what salt tastes like.
Like sodium.
Didn't help, because I can't taste sodium.
It's an
I can't taste rock, so again, it's not helping me. I mean, you guys put it on everything. Yeah, as a matter of fact, those of you that live in America put too much of it on stuff, right, to your detriment. You say it tastes good on chicken, but I don't know what that means, right?
Salt tastes like dehydration.
Dehydration doesn't have a taste. It's a state of not having enough liquid in your body. Like, why can't you tell me what salt tastes like? Because in order to know what salt tastes like, what do you need to do? You have to experience it, right? Okay? We lack the words to describe something that is experiential in its nature. You just have to taste it, right? And then you can identify, oh, that's salty. Same thing goes for sweet or sour, any of these other, umami, whatever the flavor profile is. So basically mass tastes like salt is what I'm trying to say, right? We don't put into words what mass is. Matter of fact, until about 9 years ago, physicists couldn't tell you what mass was because we didn't know. But you experience your mass all the time. You are constantly pushing and pulling against your mass. And you're experiencing the mass of the earth or the mass of your backpack or the mass of your car. Like, you experience this all the time. And so you have this internal, like, experiential definition of what mass is. It's just the problem is it gets a little bit tied up with forces and weights and acceleration. We kind of have to kind of get all this separated out. So let me see if I can't help you understand kind of what mass is. And I'm going to start with something that's not very helpful, and then we're going to get to the more helpful parts. Okay, so let me give you the first definition that doesn't help very much. What did I do? I rearranged things, didn't I? Okay, I just divided both sides by A. Okay, so mass is force divided by acceleration. It's a push or a pull divided by a change in motion. That doesn't make any sense. It's the thing that causes force and changes in motion to be proportional. This is how we know the car has more inertia than the bicycle. If you apply a certain amount of force to a bicycle, it'll move, right? But in order to get the car to move the same amount, to change its motion by the same amount, do you have to do more or less force? If I want to take the bike and take it from 0 to 10 miles an hour, how much force does that take compared to doing the same thing to the car to get it from 0 to 10 miles an hour? It takes a lot less force to do it with the bicycle. Why? Because its mass is less. Right? The bicycle has less mass. The car has more mass. How do you know? It takes more force to give the same acceleration. Or, if you use the same push or pull, the acceleration of the car will be less. If you take one finger and you push on the bike, you might be able to move it. But if you take one finger and push on the car, don't break your finger. Right?
When we refer to something as heavy, are we referring to the weight?
Yeah, we are. Okay. So, what are the units of acceleration? Yeah, meter per second squared, a distance per time squared. We've been up against that in other chapters, right? What are the units of mass? Yes, they're kilograms. Okay, these are the units. Okay, over here in purple. What are the units of force? The force would have to be a kilogram times a meters per second squared, because it's an m times an a, but that's not what a force is, right? But this happens to be what the units are. This gets a new name called the Newton. N-E-W-T-O-N, okay? A Newton is a kilogram meter per second squared. It is a unit of force. So if in the United States you ask somebody how much they weigh, what are they going to do? Shoot you. Yeah, first they'll assault you, and then they might tell you the number, right? But they'll tell you the number in what unit? Pounds. Pounds is the imperial or stupid unit system unit for forces. So when I say I weigh 175 pounds, what I'm trying to tell you is that the earth is pulling down on me with 175 pounds. And now that we know about Newton's third law, the earth is also, or I'm also pulling up on the Earth with 175 pounds. Okay. If you did the same thing in Europe, they would answer in kilograms. But the kilogram is not a force. What is it a unit of? Mass. If you want to know their weight, then they would have to answer in newtons. Okay? But they usually don't. They usually go for kilograms. Mass is the thing that doesn't change no matter where you are in the universe. But if we go to the moon, something does change. The force of gravity acting on you, because the moon has less gravity, which means that your weight on the moon is less. Your mass stays the same, but your weight changes because the moon is pulling on you less. The acceleration, the free fall acceleration on the moon is also lower. So this gets tangled up, right? And carefully thinking through all of these things is very important. Does anybody know what the stupid unit system unit is for mass? If a force is in pounds, does anybody know what the... Stones is the English, like UK unit that's actually not the original unit. It's the slug. I mean, are we talking brown or banana slug, right? Like it's slug as in like a slug of metal, like a little sample or portion of a piece of metal, often called a slug. Yeah, so we don't obviously use that one, hardly at all, right? But we got to be careful. Okay, so there is a way to find our weight, right? Our weight W, right? The force acting on us is going to be our mass times a very special acceleration, because it should be the weight that we have with gravity being the only thing acting on us. What's the acceleration that gravity gives to all objects? Little g. So, the weight of any object is just its mass times little g. In fact, if you know its weight, you can find its mass if it's sitting on the surface of planet Earth, right? Okay. But weight is a push or a pull. It's a force. Mass tastes like salt. All right, we did that. Oh, 1 Newton, this is not the exact conversion. It's close. It's about 0.22 pounds. I'm not good at remembering very many numbers. I read this one off my paper. I tend to round this in my head to a quarter, like 0.25. Because to me, quarters are kind of easier to work with, right? So if something's 4 newtons of weight or 4 newtons of force, I know that that's roughly 1 pound's worth of force, right? And I got an idea in my head of like what 1 pound is. But I'm also, by nature, I'm not a cruel person. I do try to treat people nicely and with respect, and to honor who they are as individuals. But sometimes I can't help myself. Sometimes when I'm in a certain fast food establishment, I have a bad habit of ordering a 1 Newton hamburger. It's a 1 Newton hamburger. Do you know what the sad part is? They start looking for it. They just need to come to my class. Make it all clear. Yeah, so 1 Newton's about a quarter pound. I put them out of their misery very quick, and I say, no, it's a quarter pound. And then they look at me like, call security. Okay, we did all that. Okay. Yeah, we got to do this. Okay, get your quiz sheets out. The order your book does it in, it's not wrong. I would probably do this slightly differently, but let's just talk about Newton's 4th law. And then what we're going to do on Thursday is we're going to bring vectors into all this. And we're going to start doing some calculations. It's going to be nasty. Okay? But let's just hammer out this concept and idea. And I'll write down the equation, not that it tells us exactly what the force is, okay? But so this is one way to express the force that gravity gives to all objects. And we'll delve into why it is the way it is. But let's just back up for a second. This is where the genius of Newton comes to the front. And we're sort of, as bad as the person he was, we're constrained to acknowledge that he was the first one to come up with this idea. And it's an idea that nowadays seems kind of like, well, duh. But you got to realize, before Newton, nobody was thinking this way. And after Newton, everybody started thinking this way. What did Newton discover?
Gravity.
No.
Fell on his head.
Okay, the apple story. All right. There were no apples.
It was a lie.
It's a lie. Okay?
So what,
As a matter of fact, we have no record of Newton ever being hit in the head by anything, although it would have explained a great deal if we could find out. The closest thing we have is a journal entry that was made by a friend of Newton 2 decades after Newton had come up with gravity and published it and all that kind of stuff. They were having tea together, and the friend was asking Newton, so how did you come up with this concept, this formulation of gravity? And Newton said, I often wondered at the force unseen that could pluck the apples from the trees and cause them to fall to the earth, right? Like there was was there an apple? Newton may have said some piece of fruit, an apple, whatever, right? But like, he wasn't sitting under a tree and got hit in the head and had some great epiphany. No. The genius of Newton, and this is the thing that just sends chills up and down my spine. Newton didn't discover gravity. I think gravity was discovered by the first thing that crawled out of the oceans and tripped, right? Newton had the audacity to understand that the same force that can pull an apple from a tree and cause it to fall to the ground is the same force that holds the moon in orbit around the earth. And that holds the earth in orbit around the sun. That force which fights you so hard when you're trying to get out of bed in the morning. And you're just lying there and you're like, please, gravity, this way today. Or just a little bit weaker today, right? Can you be on my side? That force is universal in its application. It works here on the surface of planet Earth, and it works on the moon, and it works on Jupiter, and it works on our galactic center. It works everywhere. Before Newton, nobody was thinking universally, like everywhere. And of course, Newton didn't know about most of the planets, and he didn't know about the galaxy or any of it. It just hadn't been discovered yet. But Newton was the first to point out that the laws that govern things that are happening right here in front of us are the same laws that govern how the universe works everywhere. It is really kind of a simple idea, but intensely profound and impactful when you start applying it in places. Notice, for this force of gravity to exist, we need how many masses? Right? One of those mass. Now, this could be like between the moon and an orbiting spacecraft. We're going to do that probably next week or the week after. You guys know about that? Artemis 2 is launching sometime within the next couple of weeks if all the tests go forward. This will be the first human crewed flight to fly around the moon since the Apollo missions, right? So we're about to do this. We're about to do a very difficult version of this. You guys are getting the simple version, but NASA figured out the hard one, right? But generally, I mean, we could, if we wanted to, we'd go ahead and say, well, big G mass of the Earth could be one of these masses, right? So specifically, if we're talking about our weight, right? One of the masses would be the mass of Earth, and what would the other mass be? Mass of us, right? Like if we're talking about our weight, okay? So mass of the Earth times mass of us, we'll just say M, okay? Divided by the distance between them squared. And this force, right, we call weight, W, right? So I think your book does F sub G for the force due to gravity. I just call it weight. The distance between the objects is the center of mass to center of mass distance. So my center of mass is roughly behind my belly button. Center mass of the Earth is 6,340 some odd kilometers that way. Okay? So it's not like the distance between the surface and me, which is only about 1.2 meters, right? It's the center of the Earth to the center of me. So if I want to calculate the gravitational force between the Earth and the moon, right? I'd have to go, the distance would have to be the center of the Earth to the center of the moon. If we're going sun and Earth, it would be the center of the sun to the center of the Earth, okay? So just so you know that distance, that R that's down there, is the center to center distance. It's also an inverse square law, which is very common in our universe. Gravity, a lot of forces do this. The intensity of light, the intensity of sound, they all obey these inverse square laws. Inverse square means if I double the distance between two objects, first of all, because it's inverse, does the force go up or down? It goes down. I'm making the big thing in the denominator bigger, right? So it goes down. But if I double it, how much did it go down by?
A quarter.
4 times, a quarter, right? Okay. If I triple it, it goes 1/9. Do you see what's happening there? You take the factor you're changing it by and you're squaring it, so it's right. So if I make the distance 4 times as big, it'll be 1/16 as strong. That's kind of what the inverse square means. And then there's big G, which I think is one of the most hilariously named constants in all of physics, right? Because big G isn't. It's 6.673 times 10 to the minus 11 newtons times meter squared over kilogram squared. Those are just the SI units to make force come out in newtons. I say big G isn't. Why do I say that?
It's times
Because it's tiny. It's a tiny number, right? 10 to the minus 12 is a trillionth, right? This is 10 to the minus 11, so just 10 trillionths, right? But this is an extremely small number. So why does gravity feel so strong? Because the mass of the Earth is so big, right? The mass of the Earth, 5.98 times 10 to the 24 kilograms. Let me leave you with this thought. What's your weight? What's weight? Force of gravity pulling on you, right? We just wrote it down there as big G, mass of the Earth times mass of us divided by the distance between us squared. Isn't it also the mass of us times the acceleration that gravity would give us if we were in free fall? We did that previously, didn't we? What cancels on both sides of that equal sign?
force.
What just disappeared? You don't matter. Wait, no, okay. You matter. Extremely. You're very important, okay? But as far as what I'm about to tell you, it makes absolutely no difference whether it's you, a mouse, an elephant, a car, a train. Doesn't matter. Because little g is what? Big G times the mass of the Earth divided by the distance or radius of the Earth, if we're going to do the surface of the Earth. What do we now know?
We don't matter.
Or matter doesn't matter.
What do we now know? We know little g for the surface of the Earth. Could we put in something else? like the mass of the moon and the radius of the moon? What about the mass of Europa and the average radius of Europa, a moon of Jupiter? What if we put in the mass of the Earth, but the radius to the top of Mount Everest? What do we now know about little g?
It changes.
It's not constant. It's different for different places and different situations. But we also know it universally. See you tomorrow. Your exam autopsy.
Mike,